Hello, so in this video we will talk about recursive relations and how to prove whether a recursive relation is the true relation or not. So let's take an example in this scenario. So what we will do is we will talk about the so-called sequence of Catalan numbers. So the sequence is defined by this relationship. It's 2n choose n divided by n plus 1. Okay, so the nth Catalan number is defined by this one. So for example, if I say C, what is the fourth Catalan number? So this is 8 choose 4 divided by 5. Okay, so by definition of combinations, this is 8 factorial divided by 4 factorial times 5 times 4 factorial again. Okay, so which is equal to 8 times 7 times 6 times 5 divided by 5 times 4 factorial. So 5 and 5 go. So this is 8 times 7 times 6 over 24. So then this is equal to 14. Okay. So this is the fourth Catalan number. Okay. Anyways, so what we want to say is now that we have a recursive definition of Catalan numbers as well. So the recursive definition goes like this. We have the kth Catalan number is equal to 4k minus 2 divided by k plus 1 times the previous Catalan number. Okay, given that the initial Catalan number is 1. Okay, now imagine that we are only given this definition and we have to come up with the closed form solution, or we have to come up with the initial expression of this sequence, which is this one. Okay, now what we will do is we will choose the mathematical induction process to prove whether this this recursive relationship gives rise to this expression or not. So what we will do, we'll do as usual, we'll say base step. Okay, our base step is, remember, for the first Catalan number is always 1, it is defined. So what we will do, we will choose n is equal to 2. Okay, so in this case C2 is equal to 4 times 2 minus 2 over 2 plus 1 times C1, which is equal to 8 minus 2 over 3 times C1, which is equal to 2. Okay, now let's put it in that equation. So C2 is equal to 4 choose 2 divided by 2 plus 1. Okay, so this 2 plus 1 is in the denominator. Okay, so 4C2 is what? Is 6 over 3, which is equal to 2. So our base step is satisfied. Now we talk about the inductive step. So in the inductive step, what we'll say that assume that ck minus 1 is given by this expression, 2k minus 2 choose k minus 1 over k. And what we want to prove, we say to prove that ck is equal to 2k choose k over k plus 1. Okay, now usually you know that in mathematical induction we assume for k and prove for k plus 1. So this is the same as, I'm just trying to simplify the expression here, because the relationship I defined was from ck to ck minus 1. So that's why I assumed for k minus 1 and I'm going to prove for k. But this is the same thing. Okay, so then let's say ck, this is equal to 4k minus 2 over k plus 1 times ck minus 1. So this is equal to, I can take this common, I can say 2 times 2k minus 1 over k plus 1 times 2k minus 2 k minus 1 over k. So then I can say 2 times 2k minus 1 over k times k plus 1 times 2k minus 2 factorial divided by k minus 1 factorial. And what is the difference between 2k minus 2 and k minus 1? 2k minus 2 is twice k minus 1. So the difference is also k minus 1 factorial. Okay. So then let me combine these two terms now. So if I combine these two terms, I will get 2 times 2k minus 1 factorial divided by. Now can I combine k and k minus 1 factorial? Of course I can. So I can say k factorial times k plus 1 times k minus 1 factorial. Okay, now remember that in the numerator what I want to do, I want to have 2k factorial. Okay, so what I will do is I will just multiply and divide by 2k. So 2k here and 2k here. So this guy will become what? This guy will become, this 2 is just here, this guy will be 2k factorial. And then this 2 will go away with this 2. Okay, and then this k and k minus 1 factorial will be k factorial. So I can say k factorial, and this is k plus 1. So this 2 goes, so this 2 is not there anymore. What is this thing? This thing is 2k, choose k, and then we have in the denominator k plus 1. So this is what we want. So again, just to repeat, we assume that the expression was true for the k minus 1th Catalan number, and using the recursive relationship we ended up proving that this is also true for the kth Catalan number. So this is a very very typical way of proving whether our recursive expression is correct or not. I mean, if we have the closed form expression, we want to check whether this is the right closed form expression or not. Okay, so just for interested viewer, there is another expression for Catalan numbers, and I'm sure there are more. Then this is k is equal to 0 to n minus 1 ck cn minus k minus 1. Okay, so this also can be proved if through mathematical induction. So this is another way to write Catalan numbers in a recursive way. Okay, but the purpose of this video was to to associate recursion with induction. So if you have a recursive relationship and you want to use mathematical induction to end up with a closed form expression which does not use recursion, then you can use this way of base and inductive step and come up with the answer. So this is it for this video. Hope you like it. Thanks for watching.